Hello there. Welcome to the Science Owl Station channel. Today we begin a quiet journey to a place you have never truly seen, even though it has always been right above you. As you settle in, imagine the moon hanging low in a dark sky, familiar and calm, its face unchanged night after night. Yet slowly, as the hours drift by, you begin to realize that this face is only half the story. There is another side, always turned away, moving in silence, keeping its distance from human eyes. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you'd like, tell me in the comments where you are listening from tonight and what time it is for you. Somewhere in the world, countless people are listening together, each of us wrapped in our own quiet moment. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. The place we're exploring is often called the dark side of the moon. But that name is one of the most persistent misunderstandings in all of astronomy. Scientists don't actually use the phrase dark side. Instead, they call it the far side of the moon. This simple distinction matters because darkness has nothing to do with it. The far side receives just as much sunlight as the side we see. It has mornings, long afternoons, and nights that stretch for nearly 2 Earth weeks. What makes it different is not light, but visibility. The reason this hidden half exists at all comes down to a gentle but powerful gravitational relationship between the Earth and the Moon. Over billions of years, Earth's gravity has slowly synchronized the Moon's rotation with its orbit. This process is known as tidal locking. It sounds technical, but the result is surprisingly simple. The moon takes the same amount of time to spin once on its axis as it does to complete one orbit around Earth. Because of that perfect match, the same lunar hemisphere always faces us. If you imagine watching the moon from far out in space, you would see it rotating. The moon does spin, but because its rotation and orbit are synchronized, from Earth's perspective it seems frozen, like a dancer turning at exactly the same pace as they circle the stage. No matter how long you wait, you never get a glimpse behind the curtain. This locked dance is not unique to our moon. Throughout the solar system, tidal locking is common. Many moons keep the same face toward their planets, shaped slowly by gravity over immense spans of time. But Earth's moon is special to us because it is so close, so familiar, and yet so quietly secretive. What we call the near side is the hemisphere that always faces Earth. It's the side etched into human history, mythology, and poetry. Ancient calendars, early telescopes, and modern lunar missions all focused there first. The far side, by contrast, remained completely unseen until the space age. For most of human existence, it was not mysterious in detail, it was simply unknowable. Another subtle difference between the near side and the far side lies in how they look from afar. The near side is marked by large, dark patches called maria. Ancient lava plains formed billions of years ago when molten rock flooded enormous basins. These dark regions create the familiar patterns many cultures imagined as faces, animals, or figures in the moon. The far side has far fewer of these lava-filled plains. From orbit, it appears brighter, rougher, and more heavily scarred. This difference leads many people to assume the far side must be fundamentally different in motion or behavior. But in truth, the moon's orbit is not perfectly circular, and its axis is slightly tilted. Because of this, careful observers on Earth can actually see about 59% of the moon's surface over time, thanks to a subtle rocking motion called libration. Even so, no human ever saw the full far side directly until spacecraft carried cameras beyond Earth's reach. The existence of a permanently hidden hemisphere shaped early scientific questions in quiet but powerful ways. Astronomers wondered whether the far side might be smoother or more chaotic, or even radically different in composition. Without data, speculation filled the silence. Some imagined vast seas, others imagined towering mountains. A few even wondered whether conditions there might somehow defy what we knew about the moon entirely. Yet all of these questions stem from one simple truth. The far side exists because gravity is patient. Tidal locking doesn't happen suddenly. It unfolds slowly, as energy is dissipated through internal friction, until rotation settles into a stable rhythm. The moon reached this state billions of years ago, long before life appeared on Earth. Dinosaurs never saw the far side. Early humans never guessed its shape. It waited quietly, unchanged, as civilizations rose and fell beneath it. Understanding what the far side is also means understanding what it is not. It is not a shadow realm. It is not permanently cold. It is not fixed in darkness. When the moon is new and invisible in Earth's sky, the far side is bathed in full sunlight. When we see a full moon glowing brightly, the far side is wrapped in darkness. Light and shadow move across it just as they do on the side we know. This hidden hemisphere is not secretive by choice. It does not turn away deliberately. It simply follows the rules of motion and gravity, rules written into the fabric of the solar system. And in doing so, it reminds us that even the most familiar objects can hold vast, unseen portions. As we continue deeper into this journey, we'll slowly peel back the layers of this unseen world. We'll explore how different its surface truly is, how violently it was shaped, and how human curiosity eventually reached around the moon to see what had always been there. But for now, it's enough to sit with the idea itself, that half of the moon has spent nearly all of history unseen, quietly circling Earth, keeping its ancient face turned away. As the far side of the moon remained unseen for so long, it naturally became a quiet home for misunderstanding. When humans cannot observe something directly, the mind fills the gap with stories, symbols, and assumptions. Over centuries, the unseen half of the moon gathered more myths than facts, not because it was strange, but because it was silent. One of the most enduring misconceptions is the idea that the far side is always dark. This belief is so widespread that it has shaped language itself. The phrase, "dark side of the moon," feels intuitive, almost poetic, suggesting eternal shadow and cold. Yet scientifically, it is simply incorrect. The far side experiences the same cycle of sunlight and darkness as the near side. Each lunar day lasts about 29 Earth days, with roughly 2 weeks of daylight followed by 2 weeks of night. Darkness there is temporary, never permanent. This misunderstanding largely comes from confusing two different ideas: darkness and invisibility. The far side is hidden from Earth, not from the sun. When the moon is full and bright in our sky, sunlight is striking the near side directly, while the far side lies in lunar night. When the moon is new and invisible to us, the situation reverses. The far side is fully illuminated, glowing quietly, though no one on Earth can see it. Another common misconception is that the moon does not rotate at all. From Earth, it can certainly appear that way. Night after night, the same familiar features stare back at us. This illusion led early observers to assume the moon was motionless, locked in place like a painted disc. In reality, the moon rotates steadily. Its rotation is simply synchronized with its orbit, an elegant balance shaped by gravity over immense time. This misunderstanding fueled early speculation that the far side might be wildly different in behavior. Some imagined extreme weather patterns, even though the moon has no atmosphere to speak of. Others thought it might be geologically unstable or somehow detached from the rest of the moon's structure. Without direct observation, imagination ran freely, unconstrained by evidence. As telescopes improved, another subtle confusion emerged. Careful observers noticed that the moon seems to wobble slightly over time. This effect, known as libration, allows us to see small portions beyond the average edge of the moon. Over months, this gentle rocking reveals about 59% of the lunar surface. To some, this suggested that perhaps the far side wasn't truly hidden after all. But even with libration, the central regions of the far side remained completely out of view until spacecraft arrived. The mystery surrounding the far side also made it fertile ground for conspiracy theories. When the first photographs were finally returned in the late 1950s, some viewers claimed they showed unnatural formations or strange patterns. Blurry images, limited resolution, and unfamiliar terrain combined to spark imaginative interpretations. A few insisted that something had been hidden from the public, even though the true explanation was far simpler. Early space cameras were primitive, and the landscape itself was unfamiliar. Another persistent myth suggests that the far side is more dangerous than the near side in some fundamental way. In reality, both hemispheres face the same harsh lunar environment. Neither has breathable air. Neither has a magnetic field strong enough to shield from radiation. Temperatures swing dramatically on both sides. The danger is not unique to the far side. It is simply part of being on the moon. The idea that the far side might somehow defy known physics also appeared in early science fiction. Writers imagined secret civilizations, strange energy fields, or portals hidden from Earth's gaze. While these stories captured the imagination, real science moved much more quietly. With each mission, the far side became less mysterious, not more, as data replaced speculation. Interestingly, even scientists once wondered whether the far side might have been shaped by unknown forces. Before direct observation, there was genuine debate about whether its surface would resemble the near side at all. Would it be smoother, more mountainous, entirely cratered? These questions were not fantasies, but reasonable scientific uncertainties based on incomplete information. What eventually dissolved most myths was not dramatic discovery, but accumulation of detail. High-resolution maps, gravity measurements, and compositional data slowly revealed a world governed by the same physical laws as everything else in the solar system. The far side was not an alien anomaly. It was simply a record keeper, preserving ancient scars that the near side had partially erased. The persistence of these misconceptions teaches a gentle lesson. Even in an age of satellites and spacecraft, language and imagery can lag behind understanding. The phrase dark side continues to be used because it feels right, not because it is accurate. Science, meanwhile, remains patient, correcting errors not through argument, but through observation. As we let these myths fade, the far side becomes something more interesting than a place of imagined danger or secrecy. It becomes a natural archive, shaped by time, gravity, and chance. And with each misconception set aside, we're able to see it more clearly, not as a shadowed realm, but as a quiet, ancient half of a familiar world. Once the myths surrounding the far side of the moon begin to fade, something more subtle and fascinating takes their place. The far side is not strange because it breaks the rules, but because it follows them in a different way. When scientists finally examined its surface in detail, they realized they were looking at a landscape that told a very different story from the one etched into the moon's familiar face. The most striking difference appears almost immediately in images from orbit. The near side of the moon is marked by vast, dark plains known as Maria, formed when ancient lava flooded large impact basins billions of years ago. These smooth regions dominate the near side's appearance and give rise to the patterns humans have imagined for thousands of years. The far side, however, is almost entirely missing these broad lava seas. Instead, its surface is brighter, rougher, and far more complex. This absence of large Maria puzzled scientists at first. The impacts that created massive basins occurred on both sides of the moon, so why did lava flood the near side so extensively, but not the far side? The answer seems to lie deep beneath the surface. The lunar crust on the far side is significantly thicker, making it harder for molten rock from the interior to break through and spread across the surface. Because lava had fewer opportunities to flow and fill basins, the far side preserved much more of its ancient topography. Craters remained sharp, ridges stayed high, valleys kept their original shapes. In a sense, the far side became a geological time capsule, locking in details that the near side partially erased under waves of molten rock. Another subtle difference is color. When viewed with instruments sensitive to mineral composition, the far side reflects slightly more sunlight. This gives it a lighter appearance overall. The lack of dark basaltic lava plains contributes to this brightness, but so does the composition of the highland rocks themselves. These regions are rich in anorthosite, a pale, reflective rock formed early in the moon's history. This contrast between the two hemispheres also hints at differences in internal heat. The near side contains higher concentrations of heat-producing elements like thorium and potassium. These elements helped keep the interior warm enough for volcanic activity to continue longer. The far side, with fewer of these elements, cooled more quickly, sealing its surface earlier and preventing widespread lava flows. Gravity played a role as well. The near side sits slightly closer to Earth, experiencing stronger gravitational effects early in the moon's history. This may have influenced how magma moved beneath the surface, encouraging eruptions on the side facing Earth. Over time, small differences became large ones, shaping two very different lunar faces. From orbit, the far side feels chaotic compared to the smoother near side. Peaks rise abruptly. Craters overlap in dense patterns. There is little visual relief from the ruggedness. Yet this chaos is not random. It is the result of billions of years of impacts accumulating on a surface that was rarely resurfaced by volcanic activity. This rugged terrain also affects how sunlight interacts with the surface. Shadows stretch long and deep across crater walls, especially near the poles. Light catches on jagged ridges, creating sharp contrasts that shift slowly over the course of a lunar day. The landscape feels dramatic, but also strangely still, frozen in a moment that has lasted for eons. What makes this surface truly remarkable is its age. Much of the far side dates back to the earliest chapters of the solar system. While Earth's surface has been constantly renewed by tectonics, erosion, and weather, the moon's far side has remained largely untouched. Each crater, ridge, and fracture is a surviving witness to an era when planets were still forming and collisions were common. The far side also challenges our sense of familiarity. We tend to assume that nearby worlds are simple extensions of what we already know. But here, just a short cosmic distance away, is a landscape that feels almost alien, not because it is strange, but because it has been allowed to remain unchanged for so long. As we move deeper into this exploration, the far side surface will continue to reveal layers of history written in stone. Its lack of Maria is not an absence, but a presence, a quiet record of what happens when a world cools early and holds on to its past. And in that silence, it offers one of the clearest windows we have into the moon's earliest days. As the moon's far side preserved its surface with little interruption, it became a canvas for one of the most intense records of cosmic violence in the solar system. Here, impacts did not fade away beneath seas of lava. They accumulated layer upon layer, leaving behind a landscape densely packed with scars. When scientists began counting craters on the far side, they quickly realized they were looking at one of the most heavily cratered regions we know. Craters blanket the far side in staggering numbers. Large ones overlap smaller ones. Older impacts are cut through by younger ones. In some regions, it is difficult to find any untouched surface at all. This density tells a quiet but powerful story. It reveals just how active the early solar system once was, when leftover debris from planet formation still roamed freely, colliding with worlds again and again. On the near side, many of these early scars were softened or erased by volcanic flooding. Lava spread across lowlands, smoothing the terrain and burying older craters beneath thick basalt. On the far side, that resurfacing rarely happened. As a result, its craters remained exposed, preserving a near-continuous timeline of impacts stretching back billions of years. Some of these craters are enormous, spanning hundreds of kilometers. Others are tiny, no wider than a city block. Together, they form a layered archive. By studying which craters lie atop others, scientists can determine their relative ages, reconstructing the sequence of events that shaped the moon long before life existed on Earth. The overlapping nature of these craters also reveals periods of intense bombardment. There was a time early in the moon's history when impacts were far more frequent than they are today. This era, often called the Late Heavy Bombardment, left deep impressions across the lunar surface. The far side, untouched by lava flows, retains some of the clearest evidence of this violent period. These impacts were not gentle. Each collision released energy equivalent to millions of nuclear explosions. Shockwaves fractured rock, melted surfaces, and threw debris across vast distances. Over time, repeated impacts shattered the upper layers of the crust into a thick blanket of rubble known as regolith. On the far side, this regolith can be especially deep, shaped by countless collisions. Craters also influence how the far side looks and feels. Their steep walls and deep floors trap shadows for long periods, especially near the poles. Even outside permanently shadowed regions, sunlight moves slowly across cratered terrain, creating dramatic shifts between light and darkness over the long lunar day. These slow-moving shadows contribute to the far side's stark, almost sculpted appearance. Interestingly, not all craters are created equal. Some have smooth floors, formed when melted rock settled after impact. Others are sharply defined, with jagged rims and central peaks formed by the rebound of the crust. These variations offer clues about the moon's internal structure and the energy involved in each collision. The sheer number of craters on the far side also makes it an ideal laboratory for understanding impact physics. With fewer resurfacing events to complicate the picture, scientists can study crater shapes, sizes, and distributions with remarkable clarity. Each crater becomes a data point in a vast experiment conducted by nature itself. In a way, the far side's cratered surface is a memory the moon refused to forget. While the near side evolved, softened, and changed, the far side stayed rigid and exposed. It absorbed the full history of impacts without covering its tracks. This makes it invaluable not only for understanding the moon, but for understanding the early solar system as a whole. As we drift further into this quiet exploration, these craters stop feeling chaotic and begin to feel deliberate. Each one marks a moment in deep time, a brief flash of violence preserved in stone. Together, they form a slow, silent chronicle of a young solar system finding its shape, written most clearly on the far side of the moon. Among the countless craters scattered across the far side of the moon, one structure stands apart in both scale and mystery. It is so vast that it reshaped an entire hemisphere, and so ancient that it predates most visible features around it. This is the South Pole Aitken Basin, a colossal scar that quietly dominates the moon's hidden face. The South Pole Aitken Basin stretches nearly 2,500 kilometers across, spanning from the moon's south pole toward its equatorial regions. To put that into perspective, it is wider than many countries on Earth. Its depth is equally remarkable, reaching more than 8 kilometers below the surrounding terrain. No other known impact structure in the solar system matches it in combined size and depth. This immense basin was formed by a single catastrophic collision early in the moon's history. An object tens of kilometers wide struck the young moon at tremendous speed, releasing an unimaginable amount of energy. The impact excavated vast volumes of crust, reshaping the surface and sending shockwaves deep into the moon's interior. For a brief moment in deep time, the moon itself rang like a bell. What makes the South Pole Aitken Basin especially valuable to scientists is what it may have uncovered. The impact was so powerful that it likely punched through the moon's crust, exposing material from the upper mantle. This means that rocks scattered across the basin may contain information about layers of the moon that are otherwise hidden far below the surface. Orbital missions have detected unusual chemical signatures within the basin. Certain minerals and elements appear in different proportions than elsewhere on the moon. These differences hint at a complex interior and support the idea that deep material was brought closer to the surface by the ancient collision. In this way, the basin acts as a natural window into the moon's internal structure. Despite its enormous size, the South Pole Aitken Basin is not immediately obvious to the naked eye. Unlike many craters with clear circular rims, its boundaries are subtle, softened by time and later impacts. It was only through detailed mapping and elevation data that scientists fully recognized its true extent. The basin reveals itself slowly, through careful observation rather than dramatic visual cues. The location of this basin also adds to its intrigue. It lies almost entirely on the far side of the moon, making it inaccessible to early lunar missions. For decades, its existence was only partially understood. Modern spacecraft, equipped with advanced instruments, finally allowed scientists to map its depth, shape, and composition in detail. There are still debates about the exact conditions of the impact that formed it. Some models suggest the impactor struck at an angle, while others propose a more direct collision. Each scenario carries implications for how energy was distributed and how deeply the moon's interior was disturbed. These questions remain open, inviting further study. The South Pole Aitken Basin may also hold clues about the moon's magnetic history. Some regions within the basin show faint magnetic signatures, raising questions about whether the moon once had a stronger magnetic field, or whether the impact itself generated temporary magnetism. These subtle signals add another layer of mystery to an already complex structure. Beyond pure science, the basin has practical significance for future exploration. Its terrain includes regions of permanent shadow near the lunar South Pole, where water ice may be trapped. At the same time, nearby elevated areas receive long periods of sunlight. This unique combination makes the region a prime candidate for future robotic and human missions. As we linger on the scale of this ancient wound, it becomes clear that the South Pole Aitken Basin is more than just a crater. It is a record of a formative moment, preserved on the moon's far side where change came slowly. In its depths and fractured rocks, the moon quietly tells the story of a time when worlds were still taking shape, and even familiar celestial bodies bore the marks of chaos. Beneath the rugged surface of the moon's far side lies another layer of difference, one that cannot be seen directly but quietly shapes everything above it. This difference is found in the moon's crust itself. Its thickness, its composition, and the slow story of how it cooled over time. Compared to the near side, the far side's crust tells a calmer, colder, and more restrained geological tale. Measurements from orbiting spacecraft reveal that the lunar crust is significantly thicker on the far side. In some regions, it may be tens of kilometers thicker than the crust beneath the near side's Maria. This added thickness acted like a sealed lid, making it more difficult for molten material from the moon's interior to rise and break through to the surface. As a result, volcanic activity on the far side was far more limited. This thicker crust helps explain the near absence of large lava plains. On the near side, thinner crust allowed magma to flow more easily, filling impact basins and creating the dark Maria we see today. On the far side, magma often stalled below the surface, cooling and solidifying before it could erupt. The surface remained dominated by ancient highlands rather than smooth volcanic plains. The chemical makeup of the far side crust also differs in subtle but important ways. It contains lower concentrations of heat-producing elements such as thorium, potassium, and certain radioactive isotopes. These elements play a crucial role in keeping planetary interiors warm. With fewer of them present, the far side lost internal heat more quickly, further reducing volcanic activity. This uneven distribution of heat-producing elements is not random. It likely formed very early in the moon's history, when the lunar interior was still molten. As the moon cooled, lighter materials floated upward to form the crust, while heavier elements sank. Slight asymmetries in this process possibly influenced by Earth's gravity or early impacts, created long-lasting differences between the two hemispheres. Orbital missions have mapped these chemical variations in remarkable detail. Instruments that measure gamma rays and X-rays emitted from the lunar surface allow scientists to identify specific elements without touching the ground. These maps reveal a far side that is chemically quieter, with fewer signs of prolonged internal heating compared to the near side. The crust's thickness also affects how the moon responds to impacts. On the far side, a thicker crust absorbs shock differently, influencing crater shapes and depths. Some craters appear deeper and more sharply defined, while others show complex internal structures. These details offer further clues about the strength and layering of the lunar crust beneath. Another consequence of this thicker crust is how gravity behaves across the moon. Variations in crustal thickness create subtle differences in the moon's gravitational field. Spacecraft flying overhead can detect these changes as slight accelerations or decelerations. By tracking these motions, scientists build detailed gravity maps that reveal hidden structures below the surface. Together, these observations suggest that the moon did not cool evenly. Instead, it developed a kind of geological imbalance early on. The near side remained warmer for longer, allowing lava to reshape its surface. The far side cooled faster, preserving its ancient features and locking in a record of early lunar history. There is still debate about why this imbalance formed in the first place. Some scientists propose that Earth's proximity influenced how heat escaped from the moon, warming the near side. Others suggest that a massive early impact redistributed material within the moon, creating long-term asymmetry. These theories are still being tested, piece by piece. What is clear is that the far side's crust is not just thicker, but quieter. It speaks in older, fainter signals, telling a story of early formation and rapid cooling. As we continue our gentle journey across this hidden hemisphere, the far side's restrained geology becomes one of its greatest strengths, preserving details that the more active near side slowly erased. Life on the moon, if it were ever attempted, would be shaped less by distance and more by temperature. On the far side, just as on the near side, heat and cold do not ease gently from one to the other. They arrive slowly, linger for long stretches of time, and then depart just as gradually, creating some of the most extreme temperature swings found on any solid world in the solar system. A single day on the moon lasts about 29.5 Earth days. This means that any given location on the far side experiences roughly 2 weeks of continuous sunlight, followed by 2 weeks of uninterrupted darkness. Without an atmosphere to trap or redistribute heat, temperatures respond directly to sunlight, rising and falling with little moderation. During the long lunar day, surface temperatures can climb above 100 degrees Celsius. Rocks bake under constant sunlight, and shadows shrink slowly as the sun creeps across the sky. There is no breeze, no cloud cover, and no cooling effect from air or water. Heat accumulates relentlessly, absorbed by the dusty regolith and exposed stone. When night finally arrives, the change is just as dramatic. With the sun gone, heat radiates back into space almost immediately. Temperatures can plunge below minus 170 degrees Celsius. The surface grows bitterly cold, and any exposed equipment must endure conditions that push materials to their limits. These freezing nights last just as long as the scorching days before them. The far side's rugged terrain amplifies these extremes. Deep craters create regions that spend long periods in shadow, even outside the polar zones. Within these shadowed pockets, temperatures can remain significantly lower than surrounding areas. Meanwhile, elevated ridges and crater rims may experience more prolonged sunlight, heating unevenly and creating sharp thermal contrasts over short distances. These extreme conditions pose serious challenges for exploration. Electronics must be carefully insulated and protected. Batteries struggle to hold charge in the cold. Mechanical components become brittle. Every mission to the far side must account for both ends of this temperature spectrum, designing systems that can survive repeated cycles of heating and freezing. Yet these same extremes also preserve ancient features. The absence of liquid water, wind, and temperature-driven erosion means that once the surface cooled, it stayed largely unchanged. Thermal cracking does occur as rocks expand and contract with temperature shifts, but this process is slow and subtle compared to the erosive forces found on Earth. Interestingly, the Moon's interior responds differently to these surface extremes. Beneath the top layer of regolith, temperatures remain far more stable. Just a few meters below the surface, the violent swings of day and night are softened. This insulating effect has important implications for future habitats, which may be placed underground to avoid the harsh surface environment. The far side's temperature patterns also influence where ice can survive. In regions where sunlight never reaches, particularly near the poles, temperatures can remain low enough for water ice to persist for billions of years. These cold traps are among the most scientifically and strategically important locations on the Moon. Despite its harshness, the far side's environment is predictable. There are no sudden storms, no seasonal shifts, and no chaotic weather patterns. Everything unfolds slowly, governed by orbital mechanics and the steady rhythm of the Moon's rotation. For explorers and scientists, this predictability offers a kind of quiet reassurance. As we drift through these extremes in imagination, it becomes clear that the far side is not hostile out of malice, but out of simplicity. It follows basic physical rules without compromise. Heat comes when the sun arrives. Cold follows when it leaves. In this stark cycle, the far side reveals the raw nature of a world without air, water, or shelter. A place where time moves slowly and change comes only through patience. Beneath the Moon's silent surface, there is a kind of movement that few people ever consider. The far side appears frozen and lifeless, yet deep inside, the Moon still responds to forces that gently flex and stress its interior. These movements are known as moonquakes, and they offer one of the most intimate glimpses into the Moon's hidden structure. Moonquakes were first detected during the Apollo missions, when astronauts placed seismometers on the lunar surface. These instruments recorded vibrations that, at first, surprised scientists. The Moon was expected to be completely still. Instead, it trembled, not violently like Earth, but subtly and persistently, as if adjusting itself very slowly. There are several types of moonquakes, each with a different cause. Some are triggered by tidal forces, as Earth's gravity gently squeezes and releases the Moon during its orbit. These tidal moonquakes tend to occur at predictable times, following a steady rhythm tied to orbital mechanics. Even on the far side, this invisible gravitational dance continues uninterrupted. Other moonquakes are caused by thermal stress. As the lunar surface heats during the long day and cools during the long night, rocks expand and contract. Over time, this repeated stretching and shrinking causes cracking and slipping within the crust. These thermal moonquakes are shallow and relatively weak, but they are frequent, quietly reshaping the surface grain by grain. There are also deeper moonquakes that originate far below the surface, perhaps hundreds of kilometers down. These are less well understood. They may be linked to internal structures slowly settling or to ancient fractures responding to long-term stress. Unlike earthquakes on Earth, which usually last seconds, moonquakes can continue for many minutes. This prolonged shaking is one of the moon's strangest characteristics. The lunar interior transmits seismic energy very efficiently. Without water or layered sediments to absorb vibrations, seismic waves bounce back and forth, echoing through the moon like sound in a vast, hollow chamber. Astronauts once described the moon as ringing like a bell. On the far side, moonquakes offer especially valuable information. Because the crust there is thicker and older, seismic waves behave differently than they do on the near side. By comparing how vibrations travel through different regions, scientists can infer variations in crustal thickness, density, and composition. Each moonquake becomes a probe, sending signals through the moon's interior. Some recordings even captured signals that did not fit neatly into known categories. These mysterious vibrations were faint, irregular, and difficult to explain. They sparked debates about whether the moon's interior is more complex than once believed, possibly containing partially molten layers or unexpected structural boundaries. Moonquakes also matter for the future. Any long-term presence on the moon, especially on the far side, must account for seismic activity, even if it is gentle. Structures would need to withstand repeated low-level shaking over many years. Understanding where and how moonquakes occur helps scientists identify safer locations for future missions. What makes moonquakes especially poetic is their contrast with the moon's outward stillness. From afar, the far side appears perfectly calm, unchanged, and unmoving. Yet beneath that quiet surface, stresses slowly build and release, responding to gravity, temperature, and time itself. As we pause here, listening in imagination to these faint tremors, the far side feels less like a dead world and more like a sleeping one. It shifts, sighs, and settles, carrying the memory of ancient forces within it. These gentle vibrations remind us that even in the deepest silence of space, nothing is ever truly still. For most of human history, the far side of the moon existed only as an idea. It circled Earth faithfully, unseen and unreachable, its surface left entirely to imagination. That changed suddenly in 1959, when a small, unassuming spacecraft quietly slipped behind the moon and gave humanity its very first glimpse of the hidden hemisphere. The spacecraft was Luna 3, launched by the Soviet Union during the early years of the space race. Compared to modern probes, Luna 3 was extremely simple. It carried a basic camera system, chemical film, and a transmitter powerful enough to send images back across hundreds of thousands of kilometers. Yet what it achieved was extraordinary. For the first time, human-made eyes looked upon a place no human had ever seen. As Luna 3 passed behind the moon, it photographed the far side through a narrow window of opportunity. The spacecraft had to work quickly, capturing images while tumbling gently through space, then developing the film on board using a rudimentary chemical process. The images were far from perfect, They were grainy, low in contrast, and partially obscured by motion blur. But they were unmistakably real. When the first images were received on Earth, scientists were stunned. The far side did not resemble the near side at all. Instead of broad, dark Maria, the photographs showed a chaotic landscape dominated by bright highlands and dense cratering. Familiar lunar patterns were gone. In their place was a rugged world that seemed almost alien, despite belonging to the same moon humans had gazed at for millennia. These early images immediately rewrote scientific expectations. Many astronomers had assumed the far side would be similar to the near side, perhaps with minor variations. Luna 3 revealed a dramatic asymmetry that demanded explanation. Why were the Maria missing? Why was the surface so heavily cratered? The far side was no longer a blank mystery, it was a puzzle. Mapping the far side from these images was a challenge. Without modern computers or digital sensors, scientists had to manually interpret distorted photographs, identifying craters and estimating their sizes and positions. Even naming features required careful consideration. New craters were given names honoring scientists, thinkers, and explorers from around the world, reflecting the global importance of the discovery. The political context of Luna 3's success cannot be ignored. In the midst of Cold War tensions, the mission served as a powerful demonstration of technological capability. Yet beyond politics, its deeper legacy was scientific. Luna 3 transformed the far side from an abstract concept into a real place, one that could be studied, measured, and eventually explored. Despite their limitations, the images from Luna 3 sparked decades of follow-up missions. They guided future spacecraft trajectories and shaped research priorities. Scientists knew now that understanding the moon required understanding both of its faces, not just the one turned toward Earth. What is perhaps most remarkable is how quietly this transformation occurred. There was no dramatic broadcast, no live video feed. The far side revealed itself slowly, line by line, as images were reconstructed and analyzed. A place hidden for billions of years entered human awareness not with spectacle, but with patience. As we drift away from that first glimpse, it's worth pausing to appreciate the moment. Luna 3 did not land. It did not sample rock or drill into the surface. It simply looked. And in doing so, it expanded the boundaries of human knowledge, turning the far side of the moon from a mystery into a destination. After Luna 3 transformed the far side of the moon from an idea into a visible landscape, human curiosity naturally followed. During the Apollo era, astronauts would come closer than ever before to this hidden hemisphere. Though no one would set foot on it, several missions passed nearby, offering fleeting but profound human perspectives on a place that had remained distant for all of history. The first humans to directly observe the far side with their own eyes were the crew of Apollo 8 in December 1968. As their spacecraft slipped behind the moon, Earth vanished from view, and radio contact fell silent. For the first time, humans experienced complete isolation from their home planet, wrapped in the shadow of the moon's far side. In that moment, the far side was no longer just unseen, it was deeply felt. This loss of communication was not symbolic. When a spacecraft passes behind the moon itself blocks radio signals from Earth. For several minutes at a time, Apollo crews were entirely cut off, unable to speak with mission control. These communication blackouts occurred every orbit, reminding astronauts that the far side was truly beyond Earth's immediate reach. Apollo astronauts described the far side as stark and unfamiliar. Without the dark Maria of the near side, the landscape looked brighter and more chaotic. Craters piled upon craters, with few smooth plains to rest the eye. From orbit, the far side felt older, rougher, and less forgiving, a place shaped by time without interruption. Despite these close encounters, no Apollo mission attempted a landing on the far side. The reasons were practical rather than philosophical. Landing on the far side would have meant complete loss of direct communication with Earth. At the time, no relay satellites existed to bridge that gap. Any emergency would unfold in silence, with no way to call for help. Navigation and safety were also major concerns. The far side's rugged terrain offered fewer flat landing sites, increasing risk. Apollo missions prioritized safety, scientific return, and political goals, all of which could be achieved more reliably on the near side. The far side, though fascinating, remained a step too far for the technology of the era. Even so, the far side played a quiet but crucial role in Apollo history. During the ill-fated Apollo 13 mission, the spacecraft used the moon's gravity to slingshot back toward Earth after an onboard explosion crippled its systems. This gravity assist maneuver took the crew around the far side, where the moon's mass bent their trajectory just enough to send them home. As Apollo 13 passed behind the moon, communication was once again lost. For a tense period, mission control could only wait. When contact was restored, the relief was immense. The far side had once again acted as both barrier and guardian, silently influencing the fate of human lives without being seen. From a scientific standpoint, Apollo missions gathered valuable data about the moon's gravity field and internal structure, including hints of mass concentrations known as mascons. These gravity anomalies affect spacecraft orbits and are tied to ancient impacts and volcanic processes. Understanding them became essential for planning future missions, especially those involving the far side. Perhaps the most lasting impact of the Apollo era was psychological. Astronauts who orbited the moon gained a unique perspective on isolation, distance, and fragility. Seeing Earth rise above the lunar horizon while circling the far side reshaped how they thought about humanity's place in the universe. The far side, in its silence, amplified that realization. Though Apollo left the far side untouched by human footsteps, it did not leave it unexplored. Each orbit, each blackout, and each observation added depth to our understanding. The far side remained distant, but no longer unreachable, waiting quietly for the next generation of explorers to arrive. After the Apollo era faded into history, the moon did not lose its quiet pull on human curiosity. Instead, attention shifted from astronauts to machines. Robotic explorers, tireless and patient, became the new eyes and ears studying the far side of the moon. With each passing decade, these missions refined our understanding, replacing early guesses with detailed maps and subtle measurements. One of the most important tools in this modern phase of exploration has been the lunar orbiter. Unlike landers or crewed missions, orbiters can survey vast regions continuously, circling the moon again and again. From this steady vantage point, they collect data across multiple wavelengths, revealing features invisible to the human eye. The far side, once seen only in blurred photographs, slowly came into sharp focus. NASA's Lunar Reconnaissance Orbiter, launched in 2009, played a particularly significant role. Equipped with high-resolution cameras, laser altimeters, and radiation detectors, it mapped the moon's surface in extraordinary detail. On the far side, it revealed razor-sharp crater rims, subtle ridges, and variations in elevation measured to within a few meters. What once looked chaotic now showed patterns and structure. Beyond imagery, orbiters measured gravity with remarkable precision. As spacecraft passed over denser or lighter regions of the moon, tiny changes in their speed revealed variations in mass below the surface. These gravity maps exposed hidden features such as buried impact basins and variations in crustal thickness. On the far side, they confirmed that the crust is generally thicker and more uniform than on the near side. Radar instruments added another layer of insight. By sending radio waves toward the surface and analyzing their reflections, scientists could probe beneath the regolith. This technique helped identify roughness, layering, and possible deposits of ice in permanently shadowed regions. Even without landing, orbiters began to sense what lay hidden below the far side's ancient crust. Modern missions also focused on radiation. Without a strong magnetic field or thick atmosphere, the moon is exposed to cosmic rays and solar particles. By measuring radiation levels across the far side, scientists gathered crucial information for future human exploration. These measurements confirmed both the risks and the predictability of the lunar radiation environment. What makes robotic exploration especially powerful is patience. Orbiters do not rush. They observe the same regions under different lighting conditions across years of slow change. On the far side, this allowed scientists to watch how shadows shift across craters, how temperatures vary, and how subtle surface changes unfold over time. Data from these missions transformed the far side into one of the best mapped places beyond Earth. In some areas, we now have more detailed topographic information than we do for remote regions of our own planet. The far side, once hidden, became one of the most precisely studied landscapes in the solar system. These robotic missions also served another purpose: preparation. Every map, measurement, and dataset feeds into plans for future landers, rovers, and eventually human presence. Understanding slopes, hazards, and resources on the far side is essential before anyone dares to return there, this time to stay longer. As machines quietly circle the moon, they continue the work begun by Luna 3, but with far greater clarity. The far side is no longer defined by mystery, but by detail. And yet, despite all this knowledge, it still feels distant and calm, a reminder that exploration does not always shout. Sometimes it simply listens. Among all modern missions to the moon, one stands as a quiet turning point in humanity's relationship with the far side. For the first time, a spacecraft would not merely observe this hidden hemisphere from above, but touch it directly. This moment arrived in January 2019, when China's Chang'e 4 mission achieved the first soft landing on the far side of the moon. Reaching the far side is not as simple as aiming a spacecraft and descending. Because the moon blocks direct communication with Earth, Chang'e 4 required a companion mission to make the landing possible at all. Months earlier, China launched the Keiqiao relay satellite and positioned it at a stable gravitational point beyond the moon. From there, Keiqiao acted as a quiet intermediary, passing signals back and forth between Earth and the lander, bridging a gap that had long kept the far side out of reach. Chang'e 4 touched down inside the von Karman crater, a vast impact structure located within the South Pole Aitken Basin. This location was carefully chosen. Scientifically, it offered access to some of the Moon's oldest material. Practically, it provided terrain suitable for a controlled landing. When the lander settled onto the surface, it marked a historic first, proof that sustained exploration of the far side was no longer just theoretical. Accompanying the lander was the Yutu-2 rover, a small, solar-powered explorer designed to roam the surrounding terrain. Compared to earlier lunar rovers, Yutu-2 moved slowly and cautiously, prioritizing longevity over speed. Over time, it became the longest operating lunar rover in history, quietly traversing the far side's ancient ground. Yutu-2's observations confirmed many expectations while raising new questions. The rover analyzed rocks and soil, detecting minerals that supported theories about deep lunar material being exposed in the South Pole Aitken Basin. These findings strengthened the idea that this region offers rare insight into the Moon's mantle and early formation. Chang'e also carried a small biological experiment, modest in scale but rich in symbolism. Seeds and insect eggs were placed in a sealed container to test whether life could begin to grow under lunar conditions. For a brief time, a cotton seed sprouted, marking the first known instance of biological growth on the Moon. Though the experiment was short-lived, it hinted at possibilities for future life support systems beyond Earth. The mission's success shifted how scientists and engineers think about the far side. What was once considered too risky or impractical suddenly became accessible. With a relay satellite and careful planning, communication barriers could be overcome. The far side was no longer isolated by physics alone. Chang'e also demonstrated a new model of exploration, one that blends scientific curiosity with long-term strategy. The mission gathered valuable data while also proving technologies essential for future bases, rovers, and possibly human missions. It showed that exploration does not always require dramatic gestures. Sometimes progress comes through quiet persistence. Internationally, the landing drew attention not just for its achievement, but for what it represented. The far side, once the last unseen face of the Moon, had finally been reached. A place hidden from human eyes for billions of years now hosted a small cluster of instruments, listening, measuring, and patiently sending data home. As Chang'e continues to operate far beyond its expected lifespan, it serves as a reminder that the far side is no longer beyond reach. It is still remote, still silent, but no longer untouched. And with that first landing, a new chapter in lunar exploration quietly began. Far from Earth's constant radio chatter, the far side of the Moon offers something almost unimaginable in the modern universe: true silence. Not the absence of sound. Space itself is silent everywhere, but the absence of electromagnetic noise. This makes the lunar far side one of the quietest natural environments in the inner solar system. From Earth, countless radio signals pour outward every second. Television broadcasts, radar pulses, satellite communications, and mobile networks flood space with interference. Even powerful radio telescopes on Earth must constantly filter out this background noise. On the Moon's near side, these signals still dominate. But on the far side, the Moon itself blocks them completely. This natural shielding creates what scientists call a radio quiet zone. For radio astronomers, it is a dream location. Signals that are impossibly faint near Earth, whispers from the earliest epochs of the universe, could potentially be detected here without interference. One of the most exciting targets for far-side radio astronomy is the so-called cosmic dark ages. This period occurred after the Big Bang but before the first stars ignited. During this time, the universe was filled with neutral hydrogen emitting extremely weak radio signals. On Earth, these signals are drowned out by human-made noise. On the moon's far side, they could finally be heard. The far side's radio silence is not only useful for studying the early universe. It is also ideal for observing low-frequency radio waves from the Sun, Jupiter, and distant galaxies. These frequencies are absorbed or distorted by Earth's atmosphere, making them nearly impossible to study from the ground. NASA and other space agencies have long considered placing radio antennas on the far side. Some concepts involve lightweight wire antennas laid directly on the surface. Others imagine crater-sized radio dishes carved into the lunar terrain itself. All would take advantage of the moon's natural shielding to listen deeper into space than ever before. Interestingly, even lunar orbiters experience this silence. When a spacecraft passes behind the moon, radio contact with Earth briefly cuts off. For astronauts during the Apollo missions, this blackout was unsettling. For scientists today, it represents a rare moment of complete radio isolation. The far side's radio quiet also has practical implications. It could serve as a testing ground for future deep space communication technologies, allowing engineers to study how systems perform without constant interference. In a sense, it offers a laboratory for both astronomy and engineering. However, this silence is fragile. As lunar exploration increases, satellites, landers, and future bases risk polluting the far side with artificial radio noise. Recognizing this, some scientists have proposed international agreements to protect portions of the far side as radio preserves, similar to dark sky reserves on Earth. The Chang'e 4 mission took advantage of this quiet environment by carrying low-frequency radio instruments. These experiments demonstrated that meaningful radio observations are indeed possible from the far side, even with relatively small equipment. In a universe filled with signals, noise, and constant activity, the far side of the moon stands apart. It is not just hidden from view, but hidden from interference. This unique silence may one day allow humanity to hear the universe's oldest stories, echoes from a time before stars, planets, or life itself existed. While much of the moon experiences extreme cycles of heat and cold, certain regions on the far side remain locked in darkness almost forever. These places exist near the lunar poles, where the sun never rises high enough above the horizon to illuminate the deepest craters. Inside them lie some of the coldest known locations in the solar system. These craters are known as permanently shadowed regions. Because the moon's axis is only slightly tilted, sunlight strikes the polar regions at very low angles. As a result, the interiors of some craters have not seen direct sunlight for billions of years. Temperatures there can drop below -230 degrees Celsius, cold enough to trap volatile substances indefinitely. For decades, scientists suspected that these frozen shadows might contain water ice. Early hints came from neutron detectors aboard orbiters, which suggested the presence of hydrogen beneath the surface. Over time, multiple missions confirmed this suspicion. Water, delivered by comets and asteroids or created by solar-wind interactions, had accumulated and remained frozen in these eternal shadows. The far side of the moon hosts many such craters, particularly near the South Pole. Some of them lie within the massive South Pole Aitken Basin, combining extreme age with extreme cold. This makes them scientifically valuable not only for studying water ice, but also for understanding how volatiles move and settle on airless worlds. Water ice on the moon is more than a scientific curiosity. It represents one of the most important resources for future exploration. Ice can be melted into drinking water, split into hydrogen and oxygen for rocket fuel, and used to support long-term human presence. In this sense, the moon's darkest places may become its most valuable. Detecting ice, however, is not simple. Permanently shadowed regions are difficult to image, and landers must operate in near-total darkness and extreme cold. Instruments often rely on radar, infrared reflections, or indirect measurements to confirm the presence of ice and other frozen compounds. Some studies suggest that the ice is not evenly distributed. Instead, it may exist as thin layers mixed with lunar soil, or as concentrated patches clinging to crater walls and floors. This variability complicates plans for extraction, but also reveals a dynamic history shaped by impacts, temperature changes, and solar radiation. The far side's isolation adds another layer of challenge. Communication with Earth requires relay satellites, and rescue or resupply missions would be more complex. Yet these same challenges make the far side an attractive testing ground for advanced autonomous systems and long-duration operations. There is also a poetic contrast at play. In the brightest object in Earth's night sky, some of the darkest places hold the key to humanity's future beyond Earth. Frozen water, locked away in silence and shadow, may one day support explorers standing only a few kilometers away under relentless sunlight. As research continues, permanently shadowed craters on the far side are shifting from obscure curiosities to strategic assets. They remind us that exploration is often about finding value where conditions seem most hostile. Looking toward the future, few locations in the solar system offer as much scientific promise as the far side of the moon. Beyond its silence and isolation, it provides a uniquely stable platform for astronomy, one that could transform how humanity studies the universe. Unlike Earth, the moon has no atmosphere. There are no clouds, no weather, and no atmospheric distortion. On the far side, this advantage is combined with natural shielding from Earth's radio emissions. Together, these conditions create an ideal environment for observing the cosmos with unprecedented clarity. One of the most compelling ideas is the construction of radio telescopes designed specifically for low-frequency observations. These frequencies are blocked or heavily distorted by Earth's ionosphere, making them nearly impossible to study from the ground. On the far side, they could be observed directly, opening a new window into the universe. Such telescopes could study the formation of the first stars and galaxies by detecting faint signals from neutral hydrogen in the early universe. These observations would help answer some of cosmology's biggest questions: how structure formed, how matter evolved, and what the universe looked like before it became illuminated by stars. The far side also offers potential advantages for optical and infrared astronomy. The moon's slow rotation provides long, uninterrupted nights, allowing telescopes to observe the same region of space for extended periods. This stability could improve the detection of faint or transient objects. Another promising application involves studying exoplanets. Telescopes placed on the far side could monitor distant stars for subtle changes in brightness, helping to identify planets orbiting them. With minimal interference and long observation windows, the precision of such measurements could exceed many Earth-based systems. Some proposed designs take advantage of the lunar landscape itself. Large craters could serve as natural foundations for massive telescopes, reducing the need for complex structural supports. In some concepts, thin reflective materials would be stretched across crater interiors, forming enormous dishes capable of collecting extremely weak signals. Robotic construction would likely precede any human involvement. Autonomous machines could deploy antennas, assemble structures, and maintain equipment in the harsh lunar environment. The far side thus becomes not just a site for observation, but a proving ground for advanced space robotics. There are also long-term benefits for planetary defense and solar monitoring. Telescopes on the far side could observe solar activity without interference from Earth-based systems, improving early warning capabilities for solar storms that threaten satellites and power grids. Despite these advantages, significant challenges remain. Power generation, thermal control, and communication all require careful planning. Relay satellites must remain operational, and equipment must survive extreme temperature swings and radiation exposure. Even so, the scientific potential is difficult to ignore. A farside observatory would not simply add to existing knowledge, it would expand the range of what is observable at all. Entire categories of cosmic signals, currently lost in noise, could finally be studied. In this sense, the far side of the moon is not just a destination. It is a lens, one that could allow humanity to see deeper into time and space than ever before. Beyond science and exploration, the far side of the moon is increasingly viewed through another lens: resources. Hidden beneath its ancient surface may lie materials that could support future space economies and long-term human presence beyond Earth. One of the most discussed resources is helium-3, a rare isotope on Earth but thought to be more abundant in lunar soil. Deposited over billions of years by the solar wind, helium-3 is considered a potential fuel for future nuclear fusion reactors. While practical fusion power using helium-3 remains theoretical, its promise has made the moon a focal point in discussions about energy security beyond Earth. The far side may host different concentrations of helium-3 compared to the near side, due to variations in surface composition and exposure history. This makes it scientifically important to map these deposits accurately before any extraction could be considered. In addition to helium-3, the lunar regolith contains a variety of useful materials. Oxygen, locked within minerals, makes up a significant portion of the moon's crust. With the right technology, it could be extracted to support breathing air or rocket oxidizer, reducing the need to launch these essentials from Earth. Metals such as iron, titanium, aluminum, and magnesium are also present in lunar soil. These materials could be used for construction, radiation shielding, and manufacturing spare parts directly on the moon. On the far side, local production could be especially valuable due to the complexity of resupply missions. Rare earth elements, essential for modern electronics, have also been detected in small quantities. While not yet proven to exist in economically viable concentrations, their presence adds to the far side's long-term strategic interest. Mining on the moon, however, is vastly different from mining on Earth. There is no atmosphere, no liquid water, and gravity is only 1/6 of Earth's. Machines must operate in extreme temperatures and abrasive dust that can damage moving parts. On the far side, Communication delays and signal blackouts add further complexity. Environmental concerns also play a role. The moon's surface preserves a record of solar system history spanning billions of years. Large-scale mining could erase or contaminate scientifically valuable sites. This has sparked debate about how to balance exploration, preservation, and utilization. Legal and ethical questions remain unresolved. International treaties prohibit national ownership of celestial bodies, but the rules surrounding resource extraction are still evolving. The far side, with its unique scientific value, is often cited in discussions about protected zones and shared heritage. Some experts suggest that early resource use will focus on supporting exploration rather than exporting materials to Earth. Water ice, oxygen, and metals could sustain lunar bases, fuel spacecraft, and enable deeper missions into the solar system. In this vision, the far side becomes part of a broader space infrastructure, not a place of exploitation but a stepping stone. Its resources, used carefully, could help humanity move farther while reducing our dependence on Earth. What was once seen as a barren, unreachable landscape may one day play a quiet but essential role in humanity's expansion into space. As plans for long-term exploration take shape, the far side of the moon is increasingly discussed as a possible location for permanent or semi-permanent human presence. While the idea may seem extreme, the unique conditions of the far side offer both compelling advantages and serious challenges. One of the strongest arguments for building a base on the far side is isolation. Shielded from Earth's radio noise, such a base could coexist with sensitive scientific instruments, including large radio telescopes. Human activity on the near side risks interfering with these observations, while the far side allows clearer separation between science and settlement. The terrain also offers natural protection. Lava tubes and deep craters could provide shelter from radiation, micrometeorites, and extreme temperature swings. Using natural structures would reduce the need to transport heavy shielding materials from Earth, significantly lowering mission costs. Power generation, however, is a major challenge. On the far side, especially near the poles, sunlight can be scarce or intermittent. Proposed solutions include nuclear power systems, long-distance power transmission from sunlit regions, or solar farms placed on elevated ridges that receive near-constant light. Communication remains another hurdle. Any human base on the far side would rely entirely on relay satellites for contact with Earth. Redundancy would be essential. The failure of a relay system could temporarily isolate astronauts, making autonomy and local decision-making critical skills. Despite these obstacles, the far side offers valuable opportunities for testing technologies needed for deep space missions. Life support systems, habitat construction, resource utilization, and autonomous operations could all be refined in an environment far harsher than low Earth orbit but closer than Mars. There is also growing interest in the far side as a destination for limited space tourism in the distant future. While not practical in the near term, the idea reflects how perceptions of the moon are changing, from a distant object to a place that could eventually host human activity. Psychological factors must also be considered. Living in permanent isolation from Earth's view, without the familiar sight of our home planet in the sky, could affect mental health. Yet some researchers suggest that this separation may also foster a stronger sense of focus and purpose among crews. International cooperation will likely play a key role. The cost and complexity of establishing a farside base exceed the capabilities of most single nations. Shared infrastructure, joint missions, and agreed-upon guidelines could help ensure peaceful and sustainable use of the region. In many ways, a farside lunar base would represent humanity's first true off-world settlement. Not just a mission destination, but a place of ongoing presence. It would push the boundaries of self-sufficiency and redefine what it means to live beyond Earth. The far side, once completely unseen and unreachable, may one day become a place where humans work, explore, and quietly adapt to a new frontier. Even after decades of study and multiple successful missions, the far side of the moon remains full of unanswered questions. In many ways, it is still the most mysterious large object in Earth's immediate cosmic neighborhood. One of the greatest puzzles is the origin of the South Pole Aitken Basin. This enormous impact structure dominates much of the far side and is the largest known crater in the solar system. Scientists continue to debate what kind of object could have created it, how deep the impact penetrated, and how it reshaped the moon's interior. Some models suggest it may have exposed material from deep within the lunar mantle, but definitive proof remains elusive. Another lingering mystery lies beneath the surface. Seismic data from past missions indicate that the moon's interior may be more complex than once believed. Differences between the near side and far side hint at asymmetric internal structures, possibly dating back to the moon's earliest formation. Why the two hemispheres evolved so differently is still not fully understood. The far side's crust is thicker, more heavily cratered, and poorer in volcanic features. These traits suggest a different thermal history, but the exact sequence of events remains unclear. Did internal heat escape unevenly? Did early impacts permanently alter one hemisphere more than the other? Each answer raises new questions. There are also mysteries tied to magnetism. While the moon lacks a global magnetic field today, patches of magnetized rock have been detected, particularly on the far side. These regions hint at a time when the moon may have had a stronger magnetic environment, but how long it lasted and why it faded are still debated. Human exploration itself raises questions about the future. How much activity can the far side sustain before its unique conditions are altered? Can scientific preservation coexist with mining, bases, and potential tourism? These are not just technical challenges, but philosophical ones. The far side also serves as a reminder of how much remains unseen. For most of human history, it was a literal blank, a face never shown. Even today, with high-resolution maps and robotic explorers, much of it remains untouched and unexplored at ground level. In the broader context of the solar system, the far side is a bridge between past and future. It preserves ancient records of impacts and formation, while also offering resources and locations that could shape humanity's next steps into space. Understanding the far side of the moon is not just about lunar science. It helps refine models of planetary evolution, impact processes, and the conditions that shape worlds across the universe. What we learn there informs how we interpret other moons, planets, and even distant exoplanets. In the end, the dark side is not dark at all. It is illuminated by questions, discoveries, and possibilities. Hidden from Earth's view, it challenges us to look deeper, think longer, and explore more carefully. The far side of the moon is no longer just a mystery behind the sky. It is a frontier, quiet, ancient, and waiting to be understood. And with that, our journey across the far side of the moon gently comes to rest. For billions of years, this hidden hemisphere orbited Earth in silence, unseen, untouched, and misunderstood. What once inspired myths and speculation has slowly revealed itself through careful observation, patient science, and quiet robotic footsteps. Yet even now, the far side refuses to give up all its secrets. It is a place shaped by ancient violence and endless stillness, a landscape where colossal impacts froze moments from the early solar system in time, where darkness preserves water, silence protects cosmic whispers, and distance forces humanity to rethink how exploration truly works. The far side reminds us that not everything important is visible at first glance. Some truths exist beyond our immediate reach, waiting for the right moment, the right tools, and the right curiosity. As technology advances, this hidden world will continue to guide our understanding, not just of the moon, but of planets, stars, and our own origins. And perhaps one day, humans will stand there themselves, looking not back at Earth, but outward into deep space. For now, it remains calm, distant, and quietly watching as it has always done. If this journey helped you relax, slow your thoughts, or drift closer to sleep, let the moon continue its orbit, steady, ancient, and unhurried, carrying these stories with it through the night. What mystery of the moon fascinates you most? And where should we travel next while the world sleeps? Rest well.